Hello everyone! Today we're looking at the history of atomic theory. You can see diagrams of the different models of the atom that we've come up with over the years. The history of atoms has been one of those voyages of discovery, one of those processes that different people down the centuries have contributed to and helped to build up the understanding of atoms that we have today. We're going to introduce some of these men and their ideas now. Sorry ladies, but for the most part they are all men. Historically, women have been kept out of scientific study, or their contributions have been overlooked or stolen. Hopefully, the future will hold different things in this regard. And of course, there will be people that we miss along the way. We're going to start in ancient Greece with Democritus. He was born in Thrace, which was in parts of modern-day Greece, Bulgaria and Turkey. Democritus was apparently known as an easygoing and friendly person, although really we don't know that much about any people from back in those times. His ideas were influential in his day, but were not liked by everyone, and Plato, one of the most famous Greek philosophers, was not a fan of Democritus, which may have led to his ideas being forgotten for some time. Democritus didn't test his ideas with any experiments. They came from conversations between him and his teacher Leucippus. Their atoms were solid lumps of matter that interacted mechanically. So, for example, an atom of metal might be a very, very tiny piece of metal, just the same as the larger piece, but this is the smallest piece that you could possibly get, and maybe they would have little hooks on them that would help connect them to other atoms of the metal. So the atoms of Democritus were like tiny mechanical devices. Next we come to Jabir bin Hayyan. Bin Hayyan was probably born in present-day Iran, but there are many ideas about his heritage in the region known as the Middle East. He wrote on many subjects, and this work is today known as the Jabirian corpus. He practiced medicine in the city of Kufa, but his political connections led to him being placed under house arrest for the last 10 years of his life. Bin Hayyan is sometimes called the father of chemistry, although at this time in history it was more commonly called alchemy. He produced the oldest known attempt to classify chemical substances, and also the oldest known recipe for an inorganic chemical compound. Also from Iran was Abu Bakr Muhammad bin Zakariya al-Razi. Al-Razi was born in the city of Ray, which was on the major trade route called the Silk Road, but he moved to Baghdad where he also practiced medicine. Like Bin Hayyan before him, he wrote on many other subjects, and his work eventually spread to Europe, probably along the Silk Road. Towards the end of his life, he went blind with the disease we call glaucoma. Al-Razi was an early experimental chemist, and he designed processes and practices that we still use today. He was able to distill alcohol, and he was a very practical form of alchemist. We should mention here that the difference between alchemy and chemistry is mostly about how you understand the idea of elements. But much of early alchemy was solid practical chemistry. Alchemy became outmoded over time, and many alchemists, including Al-Razi, clung to beliefs like cheaply turning lead into gold, which we now know to be impossible. However, alchemists did do serious work, and Al-Razi especially rejected the idea that magic was part of the process. When he was asked if he had discovered the secret to turn copper into gold, he is reported to have said that he doubted it was possible. Bin Hayyan and al-Razi did not develop the theory of atoms further themselves, but their efforts in classification and experimentation were very necessary for those that came later. They were among the first to treat the study of substances in a scientific way, and we will no doubt ignore many other steps that were taken over the next 800 years to 18th century France. Next we have Antoine Lavoisier, and this is one case where we can say with confidence that Lavoisier's wife, Marianne,
was heavily involved in his scientific work. Lavoisier was a French man with a lot of money, and he used that wealth to do many new experiments in science, especially chemistry. Unfortunately for him, his lifestyle as a rich man and a tax collector led to him being executed during the French Revolution, although they did say sorry later, which was nice of them. As I said, Lavoisier did many experiments that demonstrated that chemistry was very much a quantitative subject, meaning that if you put an exact amount in, you get an exact amount out. Before Lavoisier, alchemists had experimented and made discoveries, but none of them had worked with the idea that you can make precise calculations about chemical reactions and know exactly what your outputs will be. Lavoisier showed that in any reaction you have the same mass before and after the reaction, even if some of that mass is, say, transformed into smoke. This is called the law of conservation of mass. The Lavoisiers also discovered hydrogen and oxygen, and noticed that oxygen was very important in the process of combustion, which is burning. This led to the downfall of phlogiston theory. Until that time, people thought that things burned because they had something in them that let them burn, and this was called phlogiston. Lavoisier showed that even things that should burn would not burn unless there was oxygen present in the air.
After the Lavoisiers came Joseph Proust, also from France. He was trained as an apothecary, which is like an early pharmacist or medicine man. He worked in Spain as well as France, and he continued his chemical studies throughout his career. His belief in definite proportions did not sit well with everyone at the time, but by comparing copper carbonate from various different places, Proust was able to show that it doesn't matter where you get your copper carbonate from, you will always get exactly the same amount of copper and carbon and oxygen from any sample you might find. This was called Proust's law, although we now call it the law of definite proportions. Next we come to John Dalton, an English school teacher. He was a very quiet man, and he was described by other scientists as a very coarse experimenter, which meant he was not very precise when he ran experiments. He was a Quaker, a kind of Christian, and something else he did in his life was to estimate the heights of different mountains in the English Lake District, where he was born. Dalton was the first to propose modern atomic theory in the sense that we understand it today. Each element is made of an atom, and all atoms of any one element are indivisible and identical. Democritus would probably have agreed with that statement. However, by this time we knew that if atoms existed, they were more than just very, very small lumps of exactly the same thing. Dalton also observed that the definite proportions of Proust can always be reduced to whole number ratios. So, for example, a molecule of water always contains 1 part oxygen and 2 parts hydrogen. Although Dalton himself would not have agreed with the idea of molecules. Next on our list is Joseph Louis Gay-Lussac from France. He was the son of a doctor and a landowner. He was another French nobleman, but fortunately for him, he survived the French Revolution, and he was the one who discovered the famous H2O relationship in water. Water is 2 parts hydrogen to every 1 part oxygen. He also tested the atmosphere by taking samples at different altitudes from a hot air balloon, and he reached a height of 7,000 meters, which was the highest anyone had been at that time. Lussac was the first to start drawing the connection between the pressure, volume, and temperature of a gas. To state this formally, if mass and volume are held constant, then the gas pressure increases linearly as the temperature rises. By scientific standards, a linear relationship like this is a fairly simple equation, but it needed accurate equipment to take this data, and Lussac needed to work with carefully controlled conditions in order to draw his conclusions. Lussac also realized that if you take oxygen and turn it all into water vapor, you will have twice the volume of water vapor as you originally had of oxygen. This suggests that oxygen is dividing into two somehow. Of course, we now know that a molecule of oxygen gas is O2, but many people in that time did not believe this, and Lussac was one of the first to show evidence for the existence of something other than simple atoms.
Someone else who very much did believe in molecules was Amadeo Avogadro from Italy. He lived in Turin and seems to have been a very quiet man, but he involved himself in politics, and this led to him losing his job on a couple of occasions. His theories on the mass of gases were not accepted until after his death, possibly because, you might have noticed, all of the chemical discovery at this time was going on in France and England, and Italy was not really thought of as a great place to find scientific theories. Avogadro suggested something that Dalton would never accept: the idea that some atoms connect together and go around in groups. For example, oxygen in the air is O2, two oxygen atoms wandering around joined together. Avogadro was also the first to suggest that at a constant temperature and pressure, an equal volume of gas will have an equal number of molecules. We now know this is true, and we call it Avogadro's number. This is 6.022 times 10 to the power of 23, and that's how many molecules you will find in 1 mole of any substance. Avogadro never calculated this number. He was just the first person to say that there was such a number.
Next we come to Dmitri Mendeleev from Russia. He didn't contribute to atomic theory as such, but he did contribute to the way we organize and think about atoms in his design of the periodic table. Mendeleev's mother noticed his scientific mind very early in his life, and she traveled vast distances with him to get him into a good school, which she eventually did. Later in life he married and then divorced, and even though the Russian Orthodox Church required he wait 7 years, he didn't care about that, and he just got married again straight away. His brilliant mind was so valuable to the Tsar of Russia that not even the powerful church could touch him. One story has the Tsar saying, "I admit Mendeleev has 2 wives, but I have only one Mendeleev." Mendeleev organized the periodic table of elements roughly into the format we use today, although we have added to it over the years. There are various different arrangements of the elements that we could use, but Mendeleev had such a brilliant understanding of the subject that his expertise, and therefore his periodic table, were recognized by the scientific community at large. We're going to take an aside here to look at Mendeleev's table, because if we want to know about atoms, this table is very important to showing how we understand them. This is the table, and if you have studied it before, then just pause the video and see if you can remember any of the different groups that we divide them into. The table is divided into horizontal periods and vertical groups. The periods are connected to filling shells of electrons. Mendeleev would never have realized this at the time. He would not have believed in the idea of electrons, because he wouldn't believe in anything he couldn't see. The vertical groups are named, and they group together elements with similar chemical properties because of how many electrons they have in a shell. We're going to go through those now very quickly. The far left group is called the alkali metals, and they are all very soft and shiny, and they react very easily because they have only one spare electron that they really want to get rid of. They especially react with water, and you might have seen these metals actually catching fire and burning when you put them in water. Next we have the alkaline earth metals, which are also silvery and reactive, but not as reactive as group 1. They are also slightly harder than the alkali metals. The next groups are the transition metals, and there are many different elements in this group, but broadly they are all metallic and they are all good at conducting electricity and heat because they have a partially filled electron shell. After the metals, we have the non-metals and metalloids. Again, we find many different types of elements in this group, including most of the ones that we use in organic chemistry. For example, carbon and oxygen. On the right, we have the halogens, which are highly reactive non-metals, similar to the alkali metals, but this time they are missing just one electron that they really want to gain. And finally, on the far right, we have the noble gases, which have a completely full electron shell, and so they don't really want to react with anything. In fact, they probably would not have been known about at all in Mendeleev's day. We do have one more group to look at, and those are the lanthanides and actinides, which are found at the bottom. They are really an extension of the transition metals, and they fit between group 2 and the transition metals, but we put them down at the bottom for convenience. Mendeleev did know about the vertical groups because this is how he put the elements together. But again, he did not know that it corresponded to the electron shells, and he didn't believe in electrons at all. Let's come back to the history with Ludwig Boltzmann from Austria. Boltzmann was a physicist, and he tackled science in a very philosophical way. He wanted to get to the very foundations of our understanding. And you can see here that atomic theory moves away from chemistry and towards physics. He defended the idea of atoms when many scientists still did not believe in them, and in fact, after one of Boltzmann's talks, the great physicist Ernest Mach stood up and said simply, "I do not believe that atoms exist." Boltzmann suffered from depression, and the opposition like this to his ideas eventually led to his suicide. Sadly, it was only 2 years later that experiments proved him right. As we said, Boltzmann did not prove atoms by experiment, but his theories were of statistical mechanics, which means that we can use the ideas of statistics from mathematics to think about large numbers of atoms and the way that they work. This helped us to show how the physical qualities from the periodic table could be explained by the ideas of atoms. Boltzmann also defined the idea of entropy, which is a strange physical property that measures disorder. Next we come to Joseph John Thompson from England. He was a physicist, and again we see that the discovery of atomic theory shifts from the chemists to the physicists because we are getting to smaller and smaller scales. J.J. Thomson came from Manchester in the Midlands of England. He went on to become a professor at Cambridge, and one of his students was Ernest Rutherford, who would later hold the same job. Thomson received a Nobel Prize for his work, and his work was proving that electrons exist. He showed that cathode rays were negatively charged particles by putting a cathode ray beam through a magnetic field and seeing that the beam was attracted towards the positive electrode. As you may know, positive attracts negative, so that showed that the cathode ray was negatively charged. He also discovered the charge to mass ratio of an electron. So if you had a certain amount, say 1 gram of these cathode ray particles, he showed how much electrical charge you would have. However, he was not able to discover the mass of a single electron or the individual charge on an electron. However, his work did lead to him to develop the plum pudding model of the atom, which shows the atom as a solid positive lump, and inside that the electrons are placed as negative charges, kind of like the plums in a plum pudding. So these negative charges spread through the atom and balance out the positive charge, leading to a neutral atom overall.
Robert Millikan came from the United States. He was a professor at the University of Chicago and went on to become a director of the very famous and prestigious Caltech. He helped to write several books on education, but he was also able to work out the charge on an electron. Millikan created drops of oil and put them into an ionized gas so they became electrically charged. He then applied an electric field to these charged oil drops and was able to balance the force of gravity acting downwards so that the drops would levitate in mid-air. Now this is a pretty cool thing to be able to do anyway, but beyond that, it allowed him to calculate the charge on one electron. He knew the mass of the oil drop, he knew the strength of gravity, and he knew the strength of the electric field. With all this information, he was able to calculate the charge on a one drop. Each drop had a slightly different mass and a slightly different charge, but Millikan noticed something very important. The charge on that drop was always a whole number multiple of a fixed value. That value was 1.602 times 10 to the power of minus 19 coulombs, and he concluded that this was the fundamental unit of charge. This charge can be positive or negative. Remember that electrons are negatively charged, but either way, we call it the elementary charge.
We will now come back to Ernest Rutherford, who came from New Zealand but spent a lot of his working life in the UK and Canada. He worked on various different areas of science, but he is best remembered for discovering the nucleus. He analysed the scattering of positively charged alpha particles hitting gold foil, and he realised that most of them went straight through the gold foil and did not get scattered, or were scattered only by small amounts. You may remember that the plum pudding model of the atom was the most accepted at that time, and that had the atom as a solid positive lump with little negative electrons spread through it. But Rutherford did not see an effect that fit with this model. If the atom was a solid positive lump, surely all of the alpha particles would scatter backwards away from the gold foil when they came close to the positively charged atoms. But they didn't, they went straight through, and only a very few atoms were scattered backwards towards the detector. This suggested to Rutherford that all of the positive part of an atom was concentrated in one very small area, and he put this in the center of the atomic model and called it the nucleus. Next we come to James Chadwick from England. Chadwick worked under Ernest Rutherford at university, and he was in Germany when the First World War broke out, and he spent 4 years in an internment camp. During the Second World War, he worked in Britain on helping to make the atomic bomb, and later went to America to help with the Manhattan Project. Chadwick built on the earlier work of other scientists. He used radioactive elements to create unknown radiation by firing the radioactivity at a metal plate. He was able to show that this radiation was uncharged particles, which were named neutrons. Neutrons were found, along with positive protons, to make up the nucleus of the atom. This modified Rutherford's earlier model of the nucleus as a single positive unit, and we now knew that it was made of a cluster of subatomic particles. Now we come to Niels Bohr from Denmark, one of the most famous physicists of the 20th century. He founded the Copenhagen Institute of Physics, which still exists to this day. He was forced to flee Denmark during World War II, to Sweden, the UK, and eventually to America, where he worked on the Manhattan Project to develop the first nuclear bombs. Like many scientists, he was a peaceful man who did not think that physics should be applied to weapons of war. However, in this period of history, there were real fears that the enemy would be the first to develop nuclear bombs, and this would lead to the loss of the war. So he and many others decided to involve themselves in the Manhattan Project. However, it is the Bohr model of the atom that we remember him most for. He was the very first to quantize electron energies into set levels that cannot be changed. The Rutherford model of the atom had the nucleus, but then electrons just kind of hung out in the space around it. They did not have any fixed relationship to the nucleus. Bohr suggested that the electrons orbit the nucleus kind of like planets around the Sun, and he suggested that these orbits have exact energy levels which cannot be changed. Unfortunately, Bohr was only ever able to make his system work perfectly for hydrogen. Other elements were more complex, and the Bohr model never actually quite fit them. However, it was absolutely vital for bringing these first ideas about quantum physics into focus and allowing the rest of the scientific community to work out what was really going on. Next we come to the most famous physicist of all time, Albert Einstein from Germany. He was actually unable to find work after his graduation, and he spent much of his early career working in a patent office in Switzerland. In 1905 he got his PhD and wrote 4 of his most famous papers, which were among the most revolutionary of the time. This immediately made him a scientific superstar, and he remained one for the rest of his life. Einstein proved the existence of electrons once and for all by explaining Brownian motion in terms of statistical physics. He also used statistical mechanics that came from Boltzmann to think about atoms in a gas. He also established the equivalence of energy and matter, the very famous E=mc² equation, and he added to the theory of wave-particle duality by talking about photons of light behaving as both waves and as particles. He did many other things as well. Now we come to Louis de Broglie from France. I think I'm pronouncing his name right, although this name has been pronounced in many different ways, so who knows? He was well known in his day and made many speculations on the philosophical groundings of science, the really basic level ideas, some of which still concern physicists to this day. He also looked into Einstein's ideas of wave-particle duality, and he started to extend this idea to any kind of molecule or any kind of matter at all, even macroscopic objects that we can see in the everyday world. However, this idea was most easily applied to electrons, and this explained Bohr's idea of quantized energy levels. So instead of orbiting the nucleus in a circular path like a planet, the idea was that maybe electrons went around the nucleus in waves, and that wave had to start and finish at the same place, so you could only have a whole number of wavelengths around the nucleus. Now, in fact, it is still not true to say that electrons orbit like planets, even planets with wave-like orbits. However, this idea of standing waves was a fundamental part of wave-particle duality and forms one of the basic ideas of quantum mechanics. Finally, we have Erwin Schrödinger from Austria. He was a colourful character in his personal life, to say the least, and he had problems in Europe because of his opposition to Nazi rule in Germany. Like many at the time, he tried to appease the Nazis, to roll back his criticism and hope that they would roll back their crazy ideas. However, they didn't, and he later regretted his position and personally apologized to Einstein for not opposing the Nazis hard enough. We should mention, however, he was not alone in making this mistake. Schrödinger formalized quantum mechanics for the very first time, and he invented an equation that describes particles in wave-like terms. This is called the Schrödinger equation. He is also very well known for Schrödinger's cat, which is a metaphor, a thought experiment. There are many places you can research Schrödinger's cat online, but the idea is it shows exactly how weird the Copenhagen interpretation of quantum mechanics is. This is one of the most famous interpretations of quantum mechanics, but there are others, and even now we have not decided which one of them is absolutely correct. So that is the end of our run-through of the history of atomic theory, and just to finish off, I want to mention our latest model of the atom. We talked about the Bohr model, which has electrons orbiting the nucleus like planets, but now we have the electron cloud model, which has the nucleus in the center, just like Rutherford said, but then the electrons exist in a cloud of probability around the nucleus, and anywhere you go in that cloud you will have a percentage chance of finding an electron from a certain energy level. This could actually be anywhere in the universe, and this idea has led us to some very strange theories about how the universe works, but we are not going to go into those today. I hope you found this video interesting. If you have, maybe you could like it or possibly consider subscribing to our channel, and maybe pass this on to somebody else who might be interested in learning about the history of atoms. Thanks for watching, and bye for now.